Our subject for the next little while is going to be AC machines. AC machines are divided into three categories: three-phase motors, single-phase motors, and AC alternators. First, let's look at three-phase motors. Three-phase motors are used throughout the world as a prime mover for industry. They convert three-phase AC into mechanical energy to operate all types of machinery. Machinery such as conveyors, pumps, industrial fans and blowers, and robots and assembly line conveyors. Three-phase motors are smaller, lighter, and operate at higher efficiencies per horsepower than single-phase motors. Shown here is a 3-horsepower single-phase induction motor next to a 3-horsepower three-phase induction motor. Notice the size difference for the equivalent amount of horsepower. Three-phase motors have three basic types we're going to look at. The squirrel cage induction motor, also called SCIM, wound rotor induction motor, or RIM, and the synchronous motor. The squirrel cage induction motor comes in many different sizes, from tens of thousands of horsepower all the way down to fractional horsepower. Shown here is a 1500 horsepower SCIM next to a 3-horsepower SCIM. Here we have an exploded view of a squirrel cage induction motor. The advantages of the squirrel cage induction motor is they have a very simple design. They have a rugged construction. They require very minimal maintenance. Small size they have per horsepower. They have good speed regulation and relatively low cost compared to other three-phase motors. And with the innovations in technology, they have simple means to control speed. Here is the wound rotor induction motor, or RIM. The main difference between this and the squirrel cage is this has a wound rotor with windings in it, and the windings are brought out through slip rings and brushes. Here we have an exploded view of a synchronous motor. These three-phase motors all use the same basic design for the stator windings and operated on the same principle of a rotating magnetic field. The difference is how the rotor operates. Wound rotor motor and squirrel cage motor utilize electromagnetic induction. Nikola Tesla patented them as a rotating transformer. Synchronous motors require an external DC power to the rotor. Construction of three-phase motors. Three-phase motors all have a stator, stationary part of the motor, rotor, end bells, bearings, termination box, and connection leads. The purpose of the fan and the shroud or cover of the motor is to move airflow over the surface of the motor and facilitate cooling. Shown here is a diagram showing the side view of a motor where the blue arrows are showing the airflow. The air is going to enter in through the center of the fan cover or shroud. The fan now is spinning. It's attached to the motor shaft. It moves the air, it forces the air out to the outer periphery of the fan, where it gets deflected by the shroud and redirected down the surface of the motor, cooling it off. Also, the fans and the shroud serves as a means to keep dust and debris off the surface of the motor. This cutaway view of the motor shows the air entering the center of the shroud, spread out from the fan and over the surface of the motor, cooling it. The Canadian Electrical Code requires all motors have enclosure markings on them, whether it be drip-proof, weatherproof, or totally enclosed. As shown here is if the motor is designated drip-proof, it must have a DP on its nameplate, weatherproof WP, and totally enclosed must have a TE on the nameplate. If we look at this totally enclosed fan-cooled motor, the TE, totally enclosed, FC is another abbreviation for fan-cooled, is on the nameplate for this motor. Note where the arrow's pointing. The open drip-proof motor, as shown here, does not have external fans. The blades attached to the rotor internal to the motor act as a fan, drawing air in through the ends of the motor, as the arrows are pointing, and then it circulates it through the motor, and then it vents and exhausts out the sides and the bottom of the motor. End bells. End bells are used to support the bearings and align the motor shaft. They're designed to suit different types of environments that the motor may operate in. They often have lubrication pathways in them to help facilitate the lubrication of the bearings that are on the rotor shaft. Here's two different types of end bells. On the left we have the open drip proof style, and on the right we have a TEFC, totally enclosed fan cooled style. Now you can tell here in the middle of the TEFC you have a precision machine surface where the bearings are going to sit in, and that's critical to make sure that the alignment of the shaft for the motor stays true. The end bells also can have slightly different designs for some of these TEFCs. We have on the left, we have a totally enclosed fan-cooled style frame, and then on the right we have the same totally enclosed fan-cooled style frame, but it has a C flange, we call it mount on it. That's for mounting bearings. Motors have a few different types of bearings depending on the application. We have bushings, ball bearings, and roller bearings. The bushings are for smaller horsepower motors and cheaper motors. You'll see these in the average furnace fan or some of the more residential motors you're going to see operate. Some of the bushings are like the lower one here, where it's got lubrication impregnated into it. Those black dots are actually a lubricant, so as the bushing wears, it'll self-lubricate. Here we have a ball bearing. Now, ball bearings are made up of an inner and an outer race, balls, a cage to hold the balls in place, and then optional grease covers. The ones with the grease covers we call greaseless bearings. Some that don't have them will require greasing at some regular interval. Always read the manufacturer's specifications on lubrication for these bearings. Here we have a roller bearing. These roller bearings are more common for high load application. So if you have a large horsepower motor that's being used for an industrial fan, let's say, on the shaft end of the motor it's quite common to see roller bearings, because as we tighten up the fan belts that are going to be connecting the motor to the fan, we can put tremendous side loading onto the motor shaft. And then if it was a ball bearing, it could easily wear out and fail. Like the ball bearing, this has an inner and outer race, a cage to support the rollers, and on smaller sizes you can see grease seals on them, but typically they require external lubrication. Again, read the manufacturer's specification on lubrication and maintenance intervals. Oh, also, on the top right there, that's a conicalized roller bearing. That's for motors that might be positioned on end, so if the shaft is pointing straight down, we need to be able to support the weight of the motor and not only whatever it's driving also. So that type of design of bearing is what that's for. Often, electricians in different industrial plants are the ones who get to be in charge of lubricating the motors. To do this, we have to identify where the lubrication points are. On this motor here, this ODP motor, we have on the back, you can just barely see it, we got a little grease nipple, and then on the front we have a grease nipple with covers on top of them to protect them from dust. Here we have a grease gun. These grease guns have a specific piston displacement in the trigger here, so it can have a very precise amount of lubricant per squeeze coming out of it. So again, read the manufacturer's specifications on lubrication intervals and the amount of grease you put into these motors. Here's a cross-sectional area what would look like down where the bearing is and the motor shaft. Here we have the bearing. Here's side view of it. We have the motor shaft would be right here. We have a clamping nut to hold the bearing in place. We have a grease nipple here. And then the white areas are open cavities here. So what we do is we'll insert the grease gun onto the, we call this a grease nipple or grease, pressure grease fitting, and we squeeze the trigger however many times the manufacturer recommends, and it will fill this cavity up with grease, and if you overfill or you have to purge the grease, some of these motors will have a drain plug out the bottom, so you can purge the old grease out if need be. Also, when lubricating these, it's easier and it's you get a better lubrication job if you do this while the motor is running, or at least turning the shaft at a decent slow RPM but a safe RPM. Now, if you over lubricate your bearing, it can cause a lot of damage. So in the previous slide we had that drain plug where we took it out so we could see and make sure we don't over lubricate. Some of the automatic lubrication systems, they take out their grease nipples, they'll put on an automatic lube system, and it just greases at a regular interval. Sometimes those systems fail, sometimes people over grease their motors, and this happens. So what happens when you over grease your motor, it will fill up the air cavities inside the motor and prevent the cooling from happening, and will cause the motor to fail. So be careful. For with bushings, lubricating bushings has a couple different methods. Here we have a felt pad that actually gets saturated with oil, and then as the shaft that goes into the middle of this bushing here spins, it'll heat up a little bit and it wicks in the oil as it's required. Here again we have that lubricant inserted bushing here, where the lubricant's actually inserted in holes inside of this bushing. As the bushing wears or heats up, the lubricant melts and then lubricates it, and it keeps itself at a nice operating level. On this side we see a grease slug or cartridge that, as the motor shaft turns here, and here's the bushing, and this has been cut away intentionally, as the motor shaft turns, it's going to wear or create friction on this grease slug here, and it's going to lubricate over time the shaft and the bushing. Here we have the stator. The stator is the stationary part of the three-phase motor. It consists of the frame, sometimes called the yoke, the core, and windings. The stator core is made of laminated sheets, all welded together. Here's the weld marks here along the side. These are sheets. Now, we use laminated sheets like we do with transformers to reduce eddy current losses. The stator windings can be Y or delta connected, and they're laid at specific intervals inside the slots in the stator core. Now we have the rotor. It's the rotating part of the motor. On the left here we have the rotor for a squirrel cage induction motor, and on the right we have the rotor for a wound rotor induction motor. Main difference between the two is the wound rotor actually has windings wound in the rotor here that are brought out to slip rings. We're going to talk about this in a little more detail later on. Here we have a synchronous motor rotor. Now, the main difference with this synchronous motor rotor and the others, this rotor has an external DC supply brought into it through slip rings, shown in the diagram in the bottom right.